This lecture is going to focus on the major points of how life on Earth originated. Currently, there is no evidence of life on other planets. This implies, but does not prove, that life originated here on Earth. The question is how could and how did this happen? Space is filled with organic molecules, but complex organic molecules are not life. So let's make a brief overview of our solar system. Our solar system includes the Sun, which is a medium-sized yellow star, 8 planets and their satellites, asteroids, comets, and meteoroids. This illustration shows us the components of our solar system and the orbits of our 8 planets. Earth is the 3rd planet from the Sun. Our inner asteroid belt orbits between Mars and Jupiter, and outside the orbit of Neptune is the Kuiper Belt, a region of icy dwarf planets, asteroids, and comets. The nebular theory explains the formation of our solar system approximately 4.6 billion years ago. The theory explains how the Sun, a thermonuclear fusion reactor, and planets formed from a solar nebula, which is a rotating cloud of gas and dust. The nebula contracted and formed a hot protosun. As rotation of the disk and collisions of matter continued, planetesimals formed. These planetesimals grew larger and became protoplanets. The protoplanets became full planets, which were complete by 4.6 billion years ago, although accretion continued for hundreds of millions of years. The planets are divided by the material they are composed of. The terrestrial planets, Mercury, Venus, Earth, and Mars, are Earth-like in their composition. They are small, dense, and rocky, with large cores of iron and nickel alloy, and have low escape velocities because of their density. This is why they orbit close to the Sun. The Jovian or Jupiter-like planets are Jupiter, Saturn, Uranus, and Neptune. They are large, low-density, gaseous, massive planets with thick atmospheres composed of hydrogen, helium, methane, and ammonia. Because they are composed of low-density material, they have high escape velocities and orbit the Sun at much greater distances than the terrestrial planets. Now let's turn our attention to the Earth's moon for a moment. The moon has an unusual history compared to many of the moons in our solar system. For one thing, it is unusually large for a moon of a terrestrial planet. Most of the moons in the solar system are attracted by gravity to the planets they orbit. The mass of the Earth is so low compared to the size of the moon that it would not have been able to attract a moon of this size, so it is evident that something different happened. The theory is that early in Earth's formation, it was hit by a Mars-sized body, a protoplanet. Portions of the Mars-sized body's core were incorporated into Earth's core, making it larger than the cores of the other terrestrial planets. Silicate materials from the impact accreted to form the moon. From analysis of rocks brought back from the moon, we know that the rocky composition of the moon is the same as the Earth. We also know that the moon has a metallic core, which is likely the remnant of what was left over from the collision. We also know the Earth has a layered composition. But how did this happen? The bombardment of Earth by planetesimals produced kinetic energy that was converted into heat. The decomposition of radioactive isotopes produced heat, and gravitational contraction both produced heat and trapped heat. All of this heat built to the point where proto-Earth melted, then differentiated based upon material density, basically took place, generating the core, mantle, and crust. This illustration is a basic diagram of the differentiated layers of Earth based upon composition. The core, both inner and outer, are made up of the densest materials, iron and nickel, which sank to the center of the planet. The mantle is made up of the rock peridotite, which is an iron and magnesium-rich silicate rock, less dense than the core, but more dense than the crust. The crust is composed of the lightest silicates that basically rose to the outer surface of the Earth where they solidified. After differentiation and planetary cooling, planetary evolution was dependent upon two things: our distance from the Sun and volcanic activity, which allows the escape of heat from Earth's interior. Accumulation of liquid water is dependent upon our distance from the Sun. Too close and water evaporates to water vapor. Too far and water freezes to water ice. Planetary size and mass are important to be able to hold on to the gases like water vapor through gravitational attraction. Planetary size and mass must also be of sufficient size to sustain our internal heat engine for a long time period. Without volcanism on Earth, we would be a frozen wasteland. This is a good approximation of what early Earth during the Hadean probably looked like. The planet was molten. There was extreme volcanism occurring, bombardment by extraterrestrial impacts, and the newly formed moon was much closer to Earth. So, where could we possibly find other life in our solar system? Mercury and the moon are too hot, too small, and volcanism ended too early. They are small with low mass and low gravity, which led to an early loss of their atmospheres. Venus is the right size and mass, but too close to the sun. The atmosphere of Venus trapped heat, producing a runaway greenhouse, causing the oceans to boil off into the atmosphere. Atmospheric water vapor photodisassociated to hydrogen and oxygen. The hydrogen escaped to space, while the oxygen reacted with rocks on the surface. And because of this, Venus has an atmosphere of carbon dioxide and sulfuric acid with surface temperatures around 450 degrees Celsius. Earth and Venus are often referred to as twin planets. They are comparable in mass, size, not too far apart in location, and comparable in composition. So why doesn't Earth have an atmosphere like Venus? The reason is because of water and its role in the carbon cycle on Earth. Water helps pull carbon dioxide out of the atmosphere and lock it away in carbonate rocks. Venus does not have water, so they do not have this carbon sink on Venus. So what about Mars? Mars is smaller than Earth and farther from the sun. It has a thin atmosphere, unlikely to support life at its surface. Water ice is found frozen in soil and crust, but it is periodically released onto the Martian surface. The geomorphology of Mars indicates it had abundant surface water in its early history, but the small size and mass of Mars resulted in an early end of volcanism and subsequent loss of its atmosphere. If life did evolve on Mars, it was early in its history. In this photo of the surface of Mars, you can see ancient river channels circled in yellow. The impact craters that cut across these channels show that the surface water was gone early in Mars history. The last round of asteroid bombardments in the solar system are basically imprinted over the top of the surface water channels. Asteroids and the moons of Jupiter and Saturn contain complex organic molecules, but no evidence of life has yet been discovered there, and the distance from the sun is great, so temperatures are very low. Recent discoveries suggest internal volcanic heat in the Jovian moon Europa and Saturn's moon Titan, that they may be great enough to sustain liquid water and possibly life. Now, impacts continue for approximately 1 billion years, defining what is called the late heavy bombardment, approximately 3.9 billion years ago. Evidence for the LHB is clearly visible on the moon. The bombardment was possibly caused by a change in Jupiter's orbit, which would have sent asteroids spinning out of orbit and into the inner solar system. We can't see the evidence on Earth because of tectonism and weathering. In this telescopic view of the lunar surface, you can see evidence of the late heavy bombardment in the lunar highlands, the light areas, which are heavily cratered. The dark areas are called the lunar mare. They are basalt flows that we know are younger than the highlands because of the lack of heavy cratering and because of cross-cutting relationships. This is the end of part 1. Now that we know how the planet originated, we will explore in part 2 how life developed.